Hello and welcome to Chapter 4 review. It is Number Theory and Cryptography. This project was put together by Carlos Fernandez, Max Woodbury, Dakota Rennemann, and Zach Tsarnas, as well as myself, Douglas Easom. Starting off with division, the definition is if there exists integers a, b, and c, where a is not equal to 0, then a divides b if b is equal to ac. The notation is as seen here, that a divides b denotes, and this is a does not divide b. So if we look at example 1, 4 does 4 divide 9? No, it does not. And if we look at example 2, 4 does divide 8. Theorem is a, b, and c are integers where a is not equal to 0. If a divides b and a divides c, then a should divide b plus c. If we look here at the example, 4 divides 8, 4 divides 12, 4 and it does divide 20. So it's true. If a divides b and a divides bc, for all integers c. So if 4 divides 8 and 4 divides 12, then 4 should divide 8 times 12, and it does. If a divides b and b divides c, then a should divide c. So if 4 divides 8 and a divides 16, then 4 should divide 16, and it does. The division algorithm is if a is an integer and d a positive integer, then their unique integers q and r, with 0 is less than r and less than d, such that a equals dq plus r. The variable definitions are as follow, and the first example is find the quotient and remainder of 80 divide 9. Solution is quotient of 80 divided 9 is 8, and the remainder is 8. Example 2, find the quotient and remainder of 75 divide 7. We see that the quotient is 10, and the remainder is 5. Moving on to section 4.2, we'll be talking about bases. We can see that positive integer b greater than 1 as a base because of this theorem. Let b1 be a positive integer greater than 1, and if n is a positive integer, it can be expressed uniquely in the form seen here. Where k is a non-negative integer, a sub 0, a sub 1 through a sub k are non-negative integers less than b, and as seen here, they're called base b digits of representation. The representation of n given in theorem 1 is called base b expansion of n is notated as seen here. We usually omit the script for 10 for base 10 expansions because it's just decimal and it's very, very redundant to repeat it over and over because it's so common in use. Most computers use binary base 2, which is zeros and ones, and they're base 2 because it's 2 to a certain power, as you'll see as we do this problem. Okay, so for the example, you can see that it starts out 0, 1, 2, 3, 4, 5, 6, 7, 8. So the 8th spot is where the power ends up. So it's a 1, so 1 times 2 to the 8th, and so on until you get down to 351. Octave expansion is the exact same way, except it's digits 0 through 7. So for the example, we have 7, 0, 1, 6. So 0, 1, 2, 3 is 8 to the 3rd, 7 times 8 to the 3rd, and then follow down until you get 3,598. Hexadecimal, very, very similar, except for the fact that it's 0 through 9, and then the letters A through F, because we don't have a decimal number for 10 through 15. So following the same thing, 2AEOB for base 16 is 1, 2, 3, 4, 5. Starting at 0, I apologize, 0, 1, 2, 3, 4. So 16 to the 4th times 2, and then follow all the way down, you'll end up getting 175,627. Base conversion. To construct the base b expansion of an integer n, divide n by b to obtain the quotient and remainder seen here. The remainder, a sub 0, is the rightmost digit of the base expansion of n. Next, divide q sub 0 by b, as seen here. The remainder, a sub 1, is the second digit from the right of the base b expansion of n. Continue by successively dividing the quotients by b, obtaining the additional base b digits as the remainder. The process terminates when the quotient is 0. So as we can see here, we go down the list, divide by 8, so we get this with the remainder, divide by 8, get the remainder, just keep moving it to the left, move to the left. We eventually get 0, so the remainder that is base 8 would be 30071, and that's their base 8 number. Okay, continuing, if we want to find the octal and hexadecimal expansions of that binary number, all we have to do is for octal, we split it into groups of 3, and then each of these groups respond to a different number. So 3, 7, 2, 7, 4 is each of these groups. And then similarly for base 16, we've split it into bases of 4, and those all refer to some other letter / number in base 16. In early 9th century BC is where actually the binary notation kind of started. It was based off this picture you see to the right, and it's actually 64 hexagrams and 8 trigrams. And basically, It's a 3-bit and a 6-bit binary numerals that were seen as early as like the dynasties in ancient China. Octal number system is used a lot in aviation. It's basically a very code that you'll see it'll send from an aircraft down, and you'll be able to, the ground radar will be able to decipher what kind of aircraft that is based on the signal that it sends. Hexadecimal was used actually as computers got bigger because of the fact that it could hold up to 16 bits instead of the normal 8, the normal 8, and that would allow for a lot more information and other stuff to be stored. And it gets the name hexadecimal because hex is 6 and decimal is 10, so it ends up being hexadecimal. These are some other common bases. They're done the exact same way as all the other ones, just slightly different numbering and stuff like that. So you can see it's 13 to the 1, 13 to 0. It's just 2 spots. And it's done. They're all done the exact same. So it's KDH, it's 0, 1, 2. Moving on to section 4.3. There's two types of positive integers. One is prime numbers and one is composite. 7 and 11 are both prime because they only divide themselves in 1. Composite 4 and 12, they divide multiple things into them, but they all have a base of prime. The theorem is every positive integer greater than 1 can be written as uniquely as prime or as a product of 2 or more primes where the prime factors are written in order of non-decreasing size. So the first example, divide by 2, divide by 2, divide by 2, you end up getting 2, 2, 2, 109, all prime numbers. So second example, same thing, 2, 2, and then 5 and 5, you get 2, 2, 5, 5, all prime numbers. So the theorem is basically that there's infinitely many prime numbers, and that's as long as Q is prime, or as the fundamental theorem of arithmetic is product of primes. So consequently, based on this theorem, there are infinitely many prime numbers. However, there's no formula to get a very, very large prime number, which makes it very hard to get an increasingly larger number of a prime. So there's not a formula. There's no way, no definite arithmetic way to algorithm to figure out an insanely large number. A modern day example would be the RSA encryption, which is basically taking 2 or more prime numbers and using it as like a public key. And the larger the prime numbers are, the harder it is to break the code per se. And people could actually send messages using these numbers to the person that only that person could decipher, figure out what it would be, because the numbers, the larger and larger, the more combinations you could possibly have. Common conjectures is every even integer n, as long as n is greater than 2, is a sum of 2 primes. It has been verified by the computer of positive integers up to 1.6 times 10 to the 18th power. The conjecture is believed to be mostly true by most mathematicians. The twin prime conjecture, however, is a conjecture that basically there's an infinite number of twin primes, which is like 3 and 5, 5 and 7, 11 and 13. And the current record for the biggest twin prime has 388,342 decimal places, which is insane. Like, I can't even possibly say that number. Moving on, we have least common multiple, which is the reverse of greatest common divisor. Let A, B, and C be positive integers. C is the least common multiple if and only if A divides C and B divides C. And if there's no smaller number that satisfies this. So basically it's just saying what is the least common ability to find multiple. So a very easy way to do this, if they're small numbers that is to just list out all the multiples of this thing. And the first number that shows on both is the least common multiple. So it's 30 shows up on both. However, if you get into really, really big numbers and more odd numbers like 773 or something like that, it wouldn't be that easier to just list out all these multiples like that. Efficient way to find GCD is to find, using the two integers, as a Euclidean algorithm. If A is greater than B and C is the remainder when A is divided by B, you end up getting this formula. So basically, you you divide by the largest number, so like 201 divided by 111, you end up getting 111, and then you get 90 left over. So you just keep doing this, keep doing this. Whenever you get 0 as the remainder, your previous number is your greatest common divisor. So in this case, it's 3. Bezout's theorem, take A and B to be positive integers, and they exist such S and T such that GCD of AB equals SA plus TB. Basically, it's just constants that would fill these spots and work so that way, so you could always solve it in this formula. It's called linear combination, by the way. You can use the Euclidean algorithm backwards to find the GCD in linear combination. You write out the terms and reminders, then you substitute each of them in previous equations. So as we can see here, you use 21 and 44. You solve it the exact same way. You end up getting 0 as your n. So 1 is the greatest common divisor. You can then use that to create two formulas. As you see here, is 2 equals 44 minus 21 times 2. 1 equals 21 minus 2 times 10. You substitute 1 into 2. You end up with this, and you can just simplify it out. Simplify, simplify, simplify. and you end up getting 1 equals 21 times 21 plus negative 10 times 44. That'll conclude the review for today. I hope it helped. I hope you enjoyed, and I will see you later.